Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is course number 4, Design with the Standard Modules, lecture number 14, Design with Decoders, for the course Digital Logic Design. The course may be known under different names like Digital Electronics or Digital Systems as well. The next slide is a disclaimer for you to read. There are many references in digital logic design, including that for Hassan, Digital Logic Design, Brown and Franczyk, Fundamentals of Digital Logic with VHDL Design, Fundamentals of Logic Design, and many others. Today we are going to talk about design with decoders and code converters, which is part of the contents of Chapter 4. As we explained in Lecture 13, a decoder is an n-input binary decoder, is a combinational module and inputs and it has 2 to the n outputs used to implement a switching function and in memory addressing. So it has many applications, including switching functions, and memory addressing to address bank in computer or a microcontroller system. Its characteristic property is that for every combination of input values, only one output is active at the same time. The outputs can be active high, logic 1, or active low, logic 0. Hence, the decoder is effectively a term generator. Its outputs are active high, each output corresponding to exactly one term. On a max term generator, and its output active, each output corresponding to exactly one max term. The decoder may have one or more input-enabled lines, which they may be active or active. So this is a block diagram for the decoder, which for n to 2 to the n, n is 2, 2 to 4, n 3, 3 to 8, and so on and so forth. X0 is the least significant bit, Xn minus 1 is the most significant bit, and we have the outputs from Y0 to Y2 to the n minus 1. If I have two inputs, X0 and X1, I have Y0, Y2, and Y3, which is to the minus 1, which is 4 minus 1. So this is the general block diagram of the decoder. So clearly we can understand that since the 2 to the n is the midterm generator, outputs are like high, and maximum output finds many applications in the synthesis of digital switching networks. Now, in the synthesis of switching networks, we will look at example by using 274LS138. So you can find the connection from 74LS138 on using data books or using just searching chip on the internet if you have access to the internet. And you can get all this from the chip. So here actually we need to implement F1, which is the sum of minterms 2, 5, 14, 15, and F2, which is the sum of the minterms 0, 2, 3, 4, 7, 8 up to 15. So the question is how we implement those functions. Now, those are inverted minterms. If we using so if we have the sum of minterm M2, M5, M14, and M15, and we put double of complement on it, one complement will generate, actually will produce M2 prime and M5 prime and M14 prime and M15 prime. And this is what we see we took M2, the output from 2 to generate M2 prime, M5 prime, M14 prime, and M15 prime taken out all to this 4 input NAND gate, and this will generate F1, and this will generate F1. The decoder itself has three inputs, and we have a 4 input A, B, C, D. We will use A to enable the decoder. The lower chip, the lower decoder is enabled A, so take a G3, while the upper will be taken to the complement to the E prime, enable E prime, which is G1, G2, because those are inverted. So when A is 0, you will activate upper decoder 3 to 8. When A is 1, you will enable the lower 3 to 8 decoder. So by this, you will generate all the midterms from M0 prime to M7 prime and 8 prime to M15 prime. Now, how we implement, since actually F2 will be the midterms, some of the midterms 0, 2, 3, 4, 7, 8, 9, 11, we look actually to F2 prime. F2 prime will be the sum of the midterm 1, see, 5, 1, 5, 12. So we have 1, 5, and 12. So those are the three signals. We have 1. So we have 1, 5, and 6, 5, 6, and 6, and 12. So if we take all those, so we take F prime, and again, if we use the complement inside, so the sum terms will become product terms. So what we need, the inverted, so we take it to an AND gate to generate F2. So what we did really, we implemented F2 prime, and we negated this again, so the AND gate changed to an AND gate. If we use an AND gate, it means we are entangling F2 prime. But we don't need F2 prime, F2, so we use an AND gate. And just Boolean algebra manipulation will show you that this is very true. So this is the explanation how the circuit is working, since the 74 is a 3 to 8 code with active low output circles indicate active low status, and the 3 enabled inputs activate the 2 active low and 1 active. So first we have to expand the 3 to 8 decoder to 4 to 16 decoder. Can enable the 74 decoder shown using significant switching variable A. If A0 is enabled, A is 1 is enabled. Hence, actually, the upper decoder generates the max terms M0 or M0 prime to M7, M7 prime, and the lower generates the max term M8 to M15. So F1 implementation, which is the sum of M2, 5, 14, 15, which is M2 prime, NAND, M5 prime, NAND, M14 prime, NAND, M15 prime. As you see, there's a complement here, which is indicate that the product is an AND gate. Okay, And the F2 ABCD, which is the sum of those matrices, which is the product term of the max terms, the product of the max terms 1, 5, 6, and 12, which is equal to M1 prime, 5 prime, M6 prime, 12. This is why we have an AND gate, while here to F2 in an AND gate. Therefore, it's 274 to generate terms or max terms, 1 for input AND gate, which is 71 half of the 70 is 21, and 1 for input AND gate, which is 1 half of the 70 is 20 to generate F2 as shown in the figure. So successfully we use decoders to implement very complicated functions. So using really integrated circuit as modules, simplify the circuit tremendously. I mean, if you implement this with using AND gates, imagine the circuit much larger than this. The next example is we would like to implement a converter XS3 to BCD Code Converter. We have the truth table, we have the decimal digit 0 to 9, then we have XS3 code and ABCD, which is 001 to 1100, which is 9, and the BCD code. We are converting XS3. We have the input ABCD and the output WXYZ with 4 K-maps, 1 for X1, I1, C, 4 K-map. And we will simplify for W, find W is the sum of term 11, 12. X is the sum of term 7, 8, 9, 10. Again, it is an 11 prime, 12 prime. So we AND gate. And the same thing with X, Y. C is the sum of n terms 4, 6, 8, 10, 12. Since this is 5 variable, 5 terms, we need 5 AND gate. If we don't have 5 AND gate, we will use 2. One is an AND gate with M12 prime. So this is what we need. An AND gate to AND the output to 4 from 4 prime, 6 prime, 8 prime, 10 prime. Then we NANDed with 12 prime to generate Z. And this is actually the implementation. The 74LS154 generates inverted midterms, and the 3 NAND gates are used to generate W, X, and Y. Based on the equation, just the output Z, we did some manipulation to the equation to use an AND gate first, and the output of the AND gate NANDed with 12 prime to NAND it to generate Z. And by this, we implemented a very complicated 3-equation with modular decoder, a single chip 74LS154, which is a 4 to 16 decoder to enable me to implement, synthesize the converter, the code converter, ease and with much simplicity. So again, decoders are extremely useful to implement switching functions, to implement converters, to implement multi-output functions, single output function regarding complexity of the function, and by using them, you can save a lot of energy, weight, and size, and the circuit will be reliable. It will be much smaller, and having a smaller circuit reduces electromagnetic interference and a lot of problems with eddy current and magnetizations and capacitance generated and any other stuff which limit the ability of the circuit sometimes to function. This is the last slide of the presentation. I would like to thank you so much. Please subscribe, and hopefully I will see you soon in the next lecture. Sincerely, Hassan.